So this is the third question in Unit 2, Worksheet 2 worksheet, and this one is talking about a bullet of mass 32 grams. Be careful with that. You'd need to obviously change that into kilograms, which would be 0.032 kilograms, is fired from a gun. The graph shows a variation of force F on the bullet with T. So we can see here that your force is changing, and therefore obviously from Newton's second law, force is equal to mass times acceleration. The acceleration is also not constant, also changing. So when we look at this first question here, we have we go down here, state and explain why it is inappropriate to use S is equal to ut plus a half at squared. Well, this A is constant. This is for uniform acceleration. So this equation is for uniform acceleration, and obviously we don't have uniform acceleration in this case. Don't have uniform acceleration or constant acceleration. Sorry about the writing again. Okay, and that's because the force is changing. Your force is changing. Force is changing, and therefore acceleration is changing, and so we don't have the uniform. Alright, then it says over here, determine the average acceleration of the bullet during the final 2 milliseconds. This little m here is a milli, so that's actually 2 times 10 to the negative 3 seconds. Must be careful of that, of the graph. So we want to determine the acceleration. Now when we look at it here, we're looking from this point over there to this point over there, So in that time period, we have got a force, and we can see there that this is almost like a straight line, and it goes from 2000 to this one over here, which is 2200. So we've got an average force there. We have an average force of about 2100 newtons, and therefore our acceleration, which will equal our force divided by our mass, divided by the mass, will equal 2100 divided by the mass, which is 0.032, and that would give us a value of about 6.6 times 10 to the 4 meters per second to the negative 2. So that will be the answer for that one. Sorry, I've written it up there. It should actually go into this spot over here. Next thing it says, show that the change in momentum of the bullet as the bullet travels along the length of the barrel is about 9 Newton seconds. Now, for this is a little bit complicated, and I hope you won't be too worried about it. It's not too difficult, but maybe a little bit complicated. We can see here that this is force here, and this is time. So we're going to get, if we find the area, that's equal to a force times the time, which is equal to the change in momentum. That's our impulse. So we actually need to find the area underneath here, and it's a matter of counting blocks. Now the first thing we're going to need to do to find that total area, because we've got a curve, it's not so easy. The first thing we need to do is, what is the area of one block? Well, the area of one block, as you can see, this is 250 newtons is that length over there, or the height, and this over here is half a millisecond. So the area of one block is going to equal 250 times 0.5 times 10 to the negative 3, because it's a millisecond, and that will give us the area of one block is 0.125 Newton seconds. So we've actually got to find the area of all of these blocks. So I'm just going to clean this out, and then we can split this up. So what I'll do is I'll split it up into areas, and what I'll do is I'll look at this from there to there and there, and then there. So I'm going to draw, well, hopefully I'll draw it. I'm not very good at drawing with this pen, but I'll basically draw a step case down here. These are supposed to be straight lines. Terrible drawing, sorry about this. So I'll find all the blocks there. In this one over here, I'm obviously going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 times 4, so that's 36 in there. And here, if I go across here, I'm going to have 8 times 2, which is 16. And here I'm going to have 7 times 1, that's 7. And here I'm going to have 4. Now, then I've got to adjust these. So when I look at this section over here, down over here, I could maybe say that's like 2 blocks there. And maybe like this is just over 1 block maybe there for that, maybe a little bit more. Here we've got just about 1 there, and maybe I can add this one and this into there, and I can make that 2, and maybe this is like 1 here. It's a bit rough, you can see, but we can add all of these up. So we're going to get 2, 3, 4, 6, 7, 14, 14, that's 20, so it's going to be 34 plus 36. We're going to get a total of about 70 blocks altogether. So if I go down here, I'm going to get about 70 times 0.125, and when I multiply that, 70 times 0.125, I get about 8.75 Newton seconds, which is approximately equal to 9. So we've worked that out. So that actually would be our change in momentum. That would be our change in momentum. So in this over here, use B2 to calculate the speed of the bullet. Well, we can use that because this is a change in momentum. We'll have to actually use that one over there. So that's the speed of the bullet. We can work because our change in momentum is equal to our mv minus u. Now, because the bullet obviously started from rest, this u is 0, and this v is our final, so it's going to be our change in b, so it's going to be 9, and we're going to divide by our mass, and our mass, as we remember, was 32 grams, or 0.032. So we divide that, 9 divided by 0.032 equals, and we get about 281. Our V is equal to about 281 meters per second to the negative 1. Alright, good. So we've got that, and then going down here we want finally to work out, well actually we've got two more things. We want to work out the average power delivered to the bullet. Now the power, remember, power is equal to work over time. Now the work is the energy. Now the energy in the bullet here is actually all kinetic energy. It's all energy due to motion. So we can actually work out the kinetic energy of this bullet. So it's a half times 0.032 times 281 squared. Let's just do that. So we square it and we times by 0.032 times by 0.5, and I get, this is my energy, about 1265.6 joules, and so my power is equal to the work, which is that energy, 1265.6 divided by the time. Now the time for this ore was 5 milliseconds, so it is 0.005. So I divide by 0.005, and I get about 253,000. I round it down to 3 significant figures, or 2 significant figures would actually be fine, watts. Okay, now in the D part over here it says use Newton's third law to explain why the gun will recoil when the bullet is fired. Now in doing this you should firstly state what is Newton's third law. So Newton's third law states that every force applied has an equal and opposite force. Therefore, the gun exerts, oops, I don't know what's happening to my pen here. My pen's just giving trouble. Let me see if I can get it working right. The gun exerts a force on the bullet, and the bullet, by Newton's 3, the bullet will exert an equal and opposite force on the gun. And so that's why the gun will go backwards. The gun will recoil backwards. So you've got 3 marks here, and you've got to make sure. So you'll get a mark for that. Then you'd show that your action force is the force of the bullet on the gun on the bullet, and then the bullet on the gun in the other direction. So you've got to make sure that you get all your marks for that. Alright, thank you very much. Any questions on this, please come and talk to me.